Hi, I'm Pintu Kumar, and today I'll be talking about a recently accepted paper titled DeGLIF for Label Noise Robust Node Classification using GNNs. GNNs, especially GCNs, performed very well on a variety of graph-related tasks, including node classification. However, GNNs assume availability to clean label data, which may not be the case with real-world data. Real-world datasets often have noisy labels due to many practical scenarios highlighted here. GCNs trained on such data show poor generalization. To tackle this, we propose an algorithm called DeGLIF, which identifies and denoises noisy nodes in a graph. In this video, I'll begin with a motivation for DeGLIF, followed by a discussion on influence function, which is a key tool used in DeGLIF. I'll then introduce DeGLIF algorithm along with the relabeling function. We'll then see the performance comparison of DeGLIF with other noise robust algorithm. Towards the end, I'll talk about some limitations to DeGLIF. In most scenarios, one can obtain a small set of clean gold standard dataset. DeGLIF requires this small set of clean validation set. The motivation for DeGLIF is as follows. If we want to identify whether a node Z is noisy or not, we train a GCN on training data and observe the validation accuracy on a small set of clean validation set. In the next step, we drop this node Z along with its associated edges and we retrain GNN and re-observe the clean validation accuracy. If the clean validation accuracy improved by dropping Z, we say that Z was noisy. In order to obtain a complete set of noisy nodes by this approach, we need to drop one node at a time and retrain GCN for every training node. This can be prohibitive even for a small sized graph. To tackle this, we use an approximation via influence function. Influence function for neural networks was introduced by Koh and Liang in 2017. The influence function approximates the change in model parameter if a training node Z is dropped from the training dataset. The terms involved here, this is the Hessian with respect to the number of parameters in the model, and this is the gradient of loss function again with respect to the model parameters. The derivation for the same is available both in this Koh and Liang paper as well as our paper. In 2023, Chen et al. Extended the idea of influence function to graph data. The derivation to both these equations is available in our paper, but to give an intuition behind the influence function for graph data, if an edge is dropped from a graph, although the edge doesn't participate directly into loss calculation, but it can alter the intermediate representation of the nodes because the message no longer flow through this edge. So this term over here captures the change in the latent representations of training nodes. If a node Z is dropped, it contributes to the change in parameter in two ways. First, the node Z is no longer part of loss calculation, and the first terms correspond to this phenomena. Secondly, if a node Z is dropped, all its associated edges are also dropped, again leading to the phenomena as we observed in case of dropping an edge, that the latent representations of other training nodes are also altered, and the second summation term captures that phenomenon. For our application, we are not just interested in change in model parameter, but we are interested in change in validation loss. The change in validation loss of a validation point Vi when a node Z is dropped is obtained as the dot product between the gradient at Vi with the I minus Z obtained in the last step. As we consider a set of clean nodes and not just one validation node, different clean validation nodes can have different opinion about Z being noisy. So we aggregate this information that leads to two variants of DeGLIF. The sum variant aggregates the sum of influence values across validation nodes, whereas the majority vote looks at the fraction of clean nodes, suggesting Z as noisy. Points that are identified as noisy are collected as a set, and similarly nodes that are identified clean. Here is an pictorial representation of end-to-end algorithm of DeGLIF. We begin with the noisy data D. A GNN called model 1 is trained on D. Using the learned parameters and a small set of clean dataset, we identify noisy nodes, which are passed to a relabeling function to produce D star. Finally, a model 2 is trained on this denoise dataset D star. The relabeling function adapted is simple yet effective. If a node is identified noisy, we look at its current label and label predicted by model 1. If they do not match, we assign label predicted by model 1 as the new label. Otherwise, we assign the second most favorable label outputted by the model 1. We compared the performance of DeGLIF with other noise robust algorithm under different noise settings and different noise levels. The result for Cora dataset at some specific noise levels are plotted over here. There are other noise levels that we have included in our paper. So we can see that for Cora dataset, our algorithm performs better for most noise levels and comparable at other noise levels. Similarly, for sightseer data also, we can see that some variant of DeGLIF performs always the best. Similarly, on Amazon photo dataset. To summarize this performance, we can say that the DeGLIF achieves better performance compared to other noise robust algorithm. We also validated this via average rank test, where DeGLIF sum achieved a rank of 1.27 as compared to its closest baseline TSS, which has achieved an average rank test score of 4.43. It is also worth mentioning that it is observed that some noise robust algorithm work well specifically for some datasets and they perform poorly on other datasets, whereas DeGLIF shows good performance across dataset. We also plotted the actual noise left in the data after an iteration of DeGLIF. So here is the noise level to begin with, and the iteration 1 denotes the noise left in the data after one iteration of DeGLIF, and we can see that in both the variants the noise reduces in the data set. Also, we tried seeing how the noise settles if we increase the number of iterations of DeGLIF, and we observed that our algorithm don't take a lot of iterations to converge. Another thing we would like to highlight is that DeGLIF is a modular algorithm. By that, what I mean is that one can use different model 1 and model 2 architecture. So in our experiments, we have used GCNs as model 1 and model 2, but one can use different architectures for model 1 and model 2. We tested this by using TSS as model 2, and we see that this hybrid model beats both TSS as well as DeGLIF in many noise cases, especially at high noise level. Finally, to end with some limitations, first limitation is that DeGLIF assumes a small set of clean data, although it is practically feasible for most scenarios, but there can be some real world scenario where that particular application cannot satisfy this demand. We'd also like to highlight that calculating influence function requires calculating and inverting an Hessian matrix. Finding a cheaper approximation is still an ongoing area of research. Thank you.